Good evening. Welcome to ASMR Chemistry. A little fun fact is that when I first started this channel, it's almost 5 years ago now, I started with calling this channel ASMR Chemistry Calligraphy because my plan was to really just focus on doing calligraphy and drawing with classic calligraphy pens. But, as things change over the years, we decide what works best for us. I have started using fountain pens more, which just are more reliable for me, and I do things other than calligraphy. So as some of you know, have been watching my channel for a while or looking at some more recent videos, I do reading sometimes, or I do shorts that are drawing and talking along with them, sometimes with music in the background. I also have molecular model kits, all sorts of things. But today is actually going to be kind of this calligraphy problem solving, and we are going to be going over balancing redox reactions. And because doing it in acidic solution, basic solution, there's a slight change when you do it in basic solution. I thought I'd make one video going over a couple examples of balancing them in acidic solution, and then I could make another video where I balance them in basic solution. So all right, let's get rolling. This is balancing. I think I'm going to write bigger than usual. Okay, balancing. Now, this is redox reactions. Balancing regular reactions, or sometimes if it's a simple redox reaction, it is done merely by mass balance. We're looking just at atoms on both sides. But redox reactions that are in aqueous and, in this case, acidic solution, you need to carry out a couple more steps because water can be involved and acid-base reactions can be involved. Okay, so let me show you how this works. Okay, I want to make sure this is focused. So, okay. All right, let's do an example. All right, where we've got permanganate. Okay, this is MnO4 minus. Now, all of these are going to be aqueous. So I'm going to start out writing this with showing that it's aqueous, but after that, I'm not going to include this, just for efficiency, and so we can focus on the balancing. Okay, so here's permanganate, and in this reaction, permanganate is reacting with the oxalate ion. Okay, so permanganate ion and oxalate ion. And redox occurs changes oxidation number. And we see that carbon dioxide occurs. Now, or forms. Carbon dioxide is in the gas phase. Okay. It bubbles away. So the very first thing we need to do is we need to assign oxidation numbers for every single element. That is going to then allow us to write out what we call half reactions. Okay, but our starting point is, what is the oxidation number of manganese here? Oxygen, everywhere we see oxygen, it will be -2. All right. If we saw oxygen in the case of a peroxide, it would be -1, but we're not seeing that here, so. Okay. So where I start, if I'm trying to figure out the oxidation number of this manganese, is I start out with what I know, and that is oxygen. Oxygen is -2 almost always when it's in a compound. The exception, as I said, is if it's in a peroxide, such as hydrogen peroxide. Very occasionally, you see it as a superoxide, or if it's elemental oxygen. But here we have oxygen as part of a polyatomic ion, and there are 4 of them. Okay, and we see that the overall charge of this permanganate is -1. So that means that if we add up all the negative charge contributions from this oxygen and we add it to the unknown oxidation number of this manganese, adding these up equals -1, the overall charge. See how that works? We have 4 oxygens. Each of them is -2. So that means we have an overall contribution of -8 charge from those oxygen ions, those oxides. Okay, this manganese has an oxidation number of X. So then the question is, what must X be so that when you add it to -8, it gives you -1? And of course, what that means is X must be +7. This is the oxidation number of manganese. Okay, we can do the same thing analogously, figuring out what the oxidation number of carbon is. Oxygen, in this case, is -2. There are 4 of them. Now there are 2 carbon atoms, so that means they're each contributing some charge, some oxidation number. We don't know yet, but we do know whatever that oxidation number is of carbon times 2, that is contributing some positive value that will offset 6 of the -8 charges from the oxygens and give an overall charge of -2. Okay, so just like we did over on this side, I'm going to put a little separator kind of here. Okay, this is what we figured out. That's +7 for the manganese. And here we now have 2X 2. Okay. So, here we have -8 contribution from the oxygen. This carbon, if it is +3 times 2 is +6. And that would leave behind a -2 once we add these together. Okay, so we solve for x is +3. Okay, so our carbon is +3 in this compound. Okay, how about this manganese? Well, it tells us right there. That is the oxidation number. I'm just going to rewrite manganese +2. Okay. And then as far as carbon and carbon dioxide, CO2, here we have oxygen behaving as it normally does. -2. And there are 2 of them. And when you add that to whatever the oxidation number is of the carbon, adding those up together gives an overall neutral, because this is a neutral molecule. Okay, so that means that oxidation number of carbon will perfectly balance out this -4 that we get from the 2 oxygens there. Okay, so that tells us x is +4. As carbon is +4. Okay, so now we are ready to assess the situation and write out the half reactions. And we can start with either the species that was oxidized or the species that was reduced. Okay. In terms of what was oxidized, what was reduced, there is a saying, a mnemonic device. Leo says, grr. Leo, losing electrons is oxidation. All right, so meanwhile, gaining electrons, shorthand here, is reduction. So if we look at manganese on this side, it's manganese +7. Look at on this side, it's manganese +2. The oxidation number has gone down. It has gotten smaller. And it does that by gaining electrons. So this is a reduction of the manganese. Okay. So let's write this reduction half reaction. Reduc half reaction. So this, we write out manganese. Now, I'm going to leave a space here for a second. And we're going to think about how many electrons it took for manganese +7 to become manganese +2. And there is just one manganese that we're looking at. Okay. So +7 to +2, that is a difference of 5. So this manganese species is gaining 5 electrons to become manganese we were able to write this half reaction. The half reactions, we show the electrons. We do not show electrons in any overall reactions. Okay, we only see them half reactions. All right. And it's 5 because we figured out manganese plus 7, if it gains 5 electrons, it goes down to plus 2. Okay. So next, we write out the oxidation half reaction. This is where we're going to see the oxidation number get larger. And we saw that with carbon. Okay, this was carbon in oxalate, and it became carbon in carbon dioxide. Carbon plus 3 going to carbon plus 4. Oxidation number is getting larger. It is going up, it is getting oxidized. That means it's losing electrons. So, unlike reduction half reaction, where it gained electrons are on the reduction, electrons are on the reaction side here. Now, for oxidation, the electrons will be on the product side. Okay, so this looks like this. This is oxalate. And we want to make sure that the carbons are balanced. Oh, I'm so sorry. I wrote chromium. Why did I do that? It's so funny. It's carbon. Thank you for your patience there. You're probably like, what is going on? Okay. So, anyway, our carbon here, C2O4. And this is CO2. Okay, but we have to have our elements balanced. Okay? Now, we can, if we would like to, write out the number of electrons that we have that are lost if we have these two. We have to have 2 carbons on this side for it to make sense. Okay, we have to have all the atoms that are not hydrogen or oxygen. We balance those. Okay. So now when we write out the number of electrons that are lost, it's based on 2 carbons. Here we didn't do anything because this manganese species has inherently just 1 manganese. Same with this one. But this one had 2, so we had to put a 2 in front. CO2. Okay. So carbon is starting out as plus 3, and then it's going to plus 4. That's why I wrote carbon, because I accidentally wrote chromium there. That's so funny. Okay. Wow, usually I catch my mistakes earlier. I must be tired, which I am. So, that's okay. So see, don't feel bad if you make mistakes like that, because I do too. Alright. So, if we had 1 carbon going from plus 3 to plus 4, that would mean it was losing 1 electron. But we have 2 carbons, so that means we're releasing losing 2 electrons. Okay, next. It is imperative that the number of electrons that are gained in the reduction half reaction equals the number of electrons that are lost in the oxidation half reaction. Okay, these will always match each other. And currently, they do not. Okay, so we think, what is a value where we can have the same number of electrons are gained equals the same number of electrons that are lost? So what we can do to achieve that is, if we multiply through 2 for the reduction half reaction and the oxidation, we multiply through by 5. Okay, and I'll show you then what we have just achieved by doing that. Okay, so our reduction half reaction now looks like this. We have 2 MnO4 permanganate plus 10 electrons. This 2 distributes all the way through. 2 manganese is 2. Okay, how about this 5 for the oxidation half reaction? 5 of these C2 minus makes 5 times 2, 10 carbon dioxides plus 10 electrons. Okay, so what we have achieved here is that we have the same number of electrons that are gained equals the same number of electrons that are lost. That has to always be true so that the electrons cancel out. And we get a net. Now, this is not a final, but we're partway there. Adding up these 2 half reactions. 2 MnO4 plus 5 C2O. And then we see what we have on this side. Men2 plus 10 CO2. Alrighty. So now, if we were to glance at this, we would see that it is not balanced in terms of oxygens that are on both sides. Okay. So next we balance the oxygens. And even if we see hydrogens at this step somewhere, we first balance the oxygens. And we do this with water. We are acknowledging oxygen atoms with water. Okay. We do this because we are acknowledging that this is all done in aqueous solution. So oxygen can and will be involved. All right. So we look at number of oxygens on this side we've got 8 there. Here we have 5 times 4. We've got 28 oxygens on this side. We've got 10 times 2. Okay, just 10 times 2. All right, 20. So that means we need to add water to this side. Okay, so I'll rewrite Mn4 plus 5 or oxalate and add. See how we have 28 on this side. We only have 20 on this side. So we need to add water to the product side. Okay, so add it to the other side, not that side. Okay, so we've got 2 manganese plus 10 CO2 plus 8. So we are going to add in the number of oxygens that we need by adding in that many water molecules, since water has 1 atom of oxygen per molecule of H2O. Okay. And finally, last thing we do is we make sure hydrogens are balanced, and we do that with H+. Okay? So final thing we do, we balance hydrogen H+. Okay, so let's take a look. No hydrogens on this side. This side, we only have the hydrogens from the water. So notice that there were 8 water molecules, but each water has 2 hydrogens per water molecule. So that means we need 16 hydrogens on this side, as we have 16 hydrogens on that side. Okay. So we are very close, and we are just going to double check everything. 4, 2 minus manganese. 2. Put this on there, plus 8 H2O. All right, let's take a look at this. We have 16 hydrogens. 16 hydrogens. Looks good. We have 8 oxygens plus 20 oxygens. We have 28 total on this side. This side, we have no oxygens there. Here, we've got 10 times 2 is 20. Plus 8 equals 8. Okay, so 28 and 28, that looks good. How about manganese? Manganese, we've got 2 of them on this side. Here, we have 2 of them. Here we don't. Okay. And finally, the carbon atoms. So here's carbon, 2 of them, times 5, so that's 10 carbon atoms on the reactant side. And on the product side, we've got just 1 place of carbons. There are 10 of them, so that is 10 carbons. 10 carbons. Carbons are balanced. Okay, so everything looks good. This is our final answer. answer. Balancing this equation in acidic solution. Yay, good job. Okay. The next one, I do not have the time to go through it, so what I'm going to do is I'm going to write it out, and I'm going to remind you the steps, and then let you do it, and then check your answer. Okay? So this problem looks like this. I'm going to put a line here. This is for you to practice. It is dichromate. Ar2O. I'm going to double check this. I got this. Just want to make sure. Yeah. Okay. I wrote it wrong in my notes, and it just didn't look right. And I was right. It is CR2O7. Okay. And when that reacts with chloride, you get a redox reaction. And so one of the products you get is chromium-3. That's like aqueous, okay, chlorine gas. Okay. So first thing you do, you go through, you identify the oxidation numbers. Some reminders. Oxidation number for an element is 0. Okay. Oxidation number for an ion in the aqueous phase is simply the charge given on that ion. So we see that here and here. And then in something like this, you need to calculate through and figure out what it would be. There are, if we look at this, oxygen minus 2. There's 7 of them. Okay. So that means there's a total contribution from oxygen of minus 14. Okay. But we just need to counteract 12 of those because the overall charge is minus 2. So if we are going to have then a cation that's plus 12, that means each chromium is plus 6. Over here, chromium is plus 3. So it's going from plus 6 to plus 3. All right, it's getting reduced. Meanwhile, chloride is minus, and it's going up. It's getting oxidized. 2, chlorine, 2. This is chlorine gas, chlorine in its elemental form. Okay. So you do that, and then you would write out the half reactions for each. You would make sure that all the elements besides the oxygen is balanced, and figure out how many electrons are gained or lost in those two half reactions. All right, then that allows you to add up the two half reactions, get a net reaction, and then balance oxygen atoms with water and balance hydrogen with H+. And then you will get this result. So if you want to pause the video now and try all the steps, and then come back and check, you could do that. Okay, here is the answer you would get. 14 Remember, these are all aqueous. 6 chloride. Alright, and then there are 2 chromium ions. 7 waters make their way in. And 3 chlorine gas molecule. Okay, do we see them all? Okay, 14 hydrogen ions, 1 dichromate ion. Oh, I put 2 plus, that should be 2 minus, so we fix that. 2 minus. I'm making so many mistakes, but I'm catching them, so that's good. Okay, dichromate, okay, plus 6 chloride gives you 2 chromate, chromium. I said chromate, I did not mean to say that, it's different. 2 chromium, 3 ions, chromium plus 3, 7 water molecules, and 3 chlorine molecules. Okay, you could call it dichlorine. All right, so all of this has been balancing redox reactions in aqueous solution. All right, so watch for a video I will make in the future that is balancing redox reactions in alkaline solution. The process is quite similar to what we did here, but what you'll be doing is adding hydroxide on one of the sides. I'll show you when you get there. Okay. But if you get this down, you will then be able to balance redox reactions, whether it's an acidic or basic solution. Once you know the extra step that you take in the basic solution. Okay. All right. Well, thank you for joining me as always. I don't think I've ever sat in front of the fire with my fountain pen and paper and done it this way before. It was very nice and relaxing and warm. It is a little bit chilly, and so making this fire, I'll show you the fire again. It's so nice. It was very nice having that accompany me, and it was very nice having you accompany me. So thank you. I am loving all the interest in chemistry, the chemistry questions, and just the general support you've all been giving is just absolutely lovely, and really tells me that what I'm doing is helpful, and it's worthwhile for a lot of you that need to learn this, want to learn this, are interested, or just enjoy the lulling speaking about chemistry. So it really makes my day if you like the video, if you share it with someone you think it would help. If you subscribe to my channel, it very much helps. Or make a comment and just say hello. I respond to every single comment. I think there's just a couple exceptions, and that's when I don't know what to say. Like if they say something I don't understand what they're actually saying, then I'm at a loss of words, and I think that's okay, right? But yeah, I enjoy it, and I thank you all for being here with me, and have a magnificent day or evening. I'll see you next time.